Able to see your screen?
Yes. Everything work?
Yes.
Is my maybe I can move this thing. Okay, is
Seems
that
nice
better?
as well. Yep, you are able to.
Okay, great. Well, yeah, I'll just get started. Thanks for the wonderful introduction. Please do stop me if there's any questions. I feel that it's a lot more useful for all of us if during the talk if I'm being confusing at all, please just let me know and I'll try and clarify anything. So yeah, I'm gonna actually be kind of taking a slight step back before I start talking about the stellar halos that I discuss in my abstract. I'm actually going to be talking a little bit more generally just about dark matter inference using observations of Milky Way analogs. So the beginning of the talk will be kind of motivation for why we use the modeling techniques that we do. And then I'll talk about a paper that I published last year using satellite galaxy observations to constrain the stellar halo mass relation. And then at the end, I'll get into the stellar halos and accretion histories. Okay, so let's see. Yeah, I work on the galaxy halo connection, which is a theory that we would like to connect what governs the dynamics of the universe to what we can actually observe. So it's a multivariate kind of abstract probability distribution function that in theory takes any, observable property of a galaxy luminosity, star formation rate, size, and tells you what the probability is of that galaxy living inside a halo with a certain mass, or concentration, or spin. And we care about this galaxy halo connection because we can use it to study the physics of galaxy formation. We can use it to infer cosmological parameters, and ultimately to probe the nature of dark matter, which is what everyone is excited about. Um, in practice, it often gets boiled down to a very simple kind of uh, I guess, single dimension, which is just stellar mass and halo mass. And so this is the very well-known stellar halo mass relation. This is taken from Risa Wechsler's and Jeremy Tinker's review paper. On the y-axis, I'm showing stellar mass normalized by halo mass. So you can kind of think of it as a kind of a star formation efficiency. And on the x-axis is halo mass. And you can see that there's this very nice kind of bump or knee around Milky Way mass halos, which means that there's kind of this peak in star formation efficiency at that mass, and to either end we have a decrease. On the higher mass end, we think that this is caused by feedback from active galactic nuclei, and on the lower mass end, we think reionization and stellar winds and supernova maybe play a role in regulating star formation. What I really care about, though, is this kind of frayed part of the stellar halo mass relation that, if you ask me, kind of looks a little bit like a frayed rope. And I want to point out that the low mass end of the stellar halo mass relation is not well constrained. And this is actually where the majority of issues with our standard cosmology lie, these so-called small scale issues. So small scale being, lower than 10 to the 11 or so in halo mass. I've just, for kind of reference, put some of the different um, naming conventions for the galaxies in this at this mass scale. But we have stuff like the cusp core controversy, which is only really observed in low mass systems. We have this idea of too big to fail, which is relevant for the Milky Way satellite population, and then of course more the planes of satellites and less the missing satellites problem nowadays. But again, all these kind of issues are relevant to these lowest mass regime. And so we want to use observations of these galaxies that I'm showing here, the bright dwarfs, the classical dwarfs, the ultra-faint dwarfs, uh, to try and clean up these small scale tensions. And so I'll just give some kind of brief insights from the standard cosmology that we assume in all of our modeling, which is CDM. The first is that structure formation proceeds hierarchically, which means that small things form first and kind of merge together to form the larger things which form later. On the figure here, I'm showing the halo mass function in black, and in purple, all of the kind of subhalo mass function scaled by their host halo masses. So, for example, the furthest dashed purple line to the right is the subhalo mass function for a 10 to the 15 mass host halo. And you can see that all of these subhalo mass functions are predicted to be Schechter functions, or just kind of a power law with an exponential decay or exponential cutoff. And to very, high approximation, these unevolved subhalo mass functions are actually self-consistent and universal in shape, which is what this figure shows nicely. And so we can use that fact a little later on when I talk about our modeling. Another really important thing to consider is that dark matter halos can their growth or their evolution can be categorized by, well, several different values, but what's common is this so-called Z50 value, or the 50% formation time. And what that means is just even for the same exact host halo mass, so let's take the Milky Way at 10 to the 12, you can have significant variance, halo to halo variance in this formation time. In other words, there's more than one way to build a Milky Way, and that's important whenever you're playing any inference games, especially if your observations are limited to just one realization of a Milky Way. So on the top panel, I'm showing these different formation paths for, again, a 10 to the 12 Milky Way. You can see there's significant variance there. And on the bottom, I'm showing the subhalo mass function for, I believe this is a 10 to 13 halo, although it doesn't matter because they're universal. In the contours, what I'm showing is a precursor to the model that I'll introduce soon, this SatGen model. And in the solid lines, I'm showing, in the data points, I'm showing a simulation. So the contours show the kind of halo to halo variance that you expect for the same exact host halo mass, again, just because of this variance in formation time. And then finally, we know that subhalos lose mass to tidal stripping, and in general, it's difficult to kind of properly resolve this thing in these massive cosmological simulations. The rate at which they lose mass is, of course, highly dependent on their orbit and the potential and their internal dynamics, what they're initialized to replicate, and also to some extent the pre-infall environment, which is something that you can only really account for in larger box simulations. And I only kind of put this slide here just to say that it's important that we're careful when linking observed properties of present-day satellite galaxies to the evolved dark matter subhalos in which they reside. This is a nice figure from a grad student in our group, Barry Chang. He shows here an idealized simulation of a subhalo losing mass to tides. And what's important about this work is it changes, the picture changes completely if you assume that the subhalo is no longer radially isotropic, which is very interesting. Okay, so that's kind of just a brief overview of what we know about the dark matter. And now we want to, again, link it to the thing that we can actually observe. And this galaxy halo connection, as you can imagine, there's a bunch of different ways to get at it. This, again, taken from the Risa and Jeremy's review, is a very nice kind of schematic of the different modeling techniques that people use. And I'm going to talk very briefly just about three of them. The first is going to be hydrodynamic simulations, which is kind of all the way to the left, the most physically and computationally expensive regime, or the most physical and computationally expensive regime. So this is basically a kind of a zoo of different simulations. On the top panel, we have the zoom-ins, both the dark matter only and the hydrodynamic, and on the bottom, we have the kind of larger box cosmological volume simulations, both the dark matter and the hydrodynamic. The point is that, again, for these small scale structures, zoom-in simulations can actually do relatively well. And it's critical for the field, but they're incredibly computationally expensive, especially when you start adding baryons to the mix. And when you do that, each simulation suite has its own, assumed particle resolution, subgrid physics, feedback prescriptions. And so there's no kind of guarantee that, one simulation is correct versus the other. And often these large scale suites are almost used as a kind of a black box, where you put in a bunch of physically motivated models and you get something out, and it's hard to kind of disentangle which property came from what assumption in the modeling. Most importantly, though, this question of kind of how many realizations can you simulate is really what I think kind of detracts from this angle of the galaxy halo connection. This is a really nice figure, or a really nice table from Christoph Engler's 2021 paper, where they show how many hosts each simulation suite has. And I want to point out that TNG50 right now at the bottom of the table only has 200 or so Milky Way-like realizations, which is state of the art. All right, the rest of these are typically less than 10 or so realizations, and that's just a testament to how computationally expensive they are. Furthermore, like I was saying, there's no kind of guarantee that these simulations will be consistent with one another, and that's exactly what a lot of people are finding in the literature. And while it's of course incredibly relevant to discuss the results from these simulations, it's also important to kind of take them with a grain of salt. So here I'm showing the stellar halo mass relation from Apostle, Elvis Latte, Auriga, and Nihao, which are some of the kind of big names, I guess, in the zoom-in simulation, hydro simulation community. Okay, so that's a little bit about hydro simulations. Most are not well suited for probing halo-to-halo variance just because it's hard to simulate, several realizations. And there's also lots of diversity across the suites because each one kind of assumes something different for how stars are built up and so on. If we go now to the other side of the spectrum, subhalo abundance modeling, this kind of is most reliant on observations, most data heavy. Oftentimes, you need to assume like a very simple monotonic relationship between galaxies and halos in terms of their abundance. So what's often done is, the most massive halo is always linked to the most massive galaxy, and you kind of just push down and propagate down through these lists of abundances that you have, which can give you some insights, but is of course incredibly simplistic. Also, kind of relevant to the other angle I was just talking about, these abundance matching results often use cosmological n-body simulations to get halo properties. So oftentimes it's the kind of mass at accretion or equivalently the circular velocity at accretion of a halo that's linked to a galaxy's luminosity or stellar mass. But when you use these massive cosmological n-body simulations, which you need for the abundances, you often run into issues with tracking these halos. And this really nice paper from Kong et al. In 2020, this year that came out, pointed out that the merger tree algorithms that people use, namely consistent trees, are basically, they can give you pretty incorrect results for actually how long these halos live inside of their, or these subhalos live inside of their hosts. And so what this is showing is a slightly novel technique they're calling bloodhound of tracking these particles across simulation snapshots. All this to say that it's a little bit complicated as soon as you start using these massive cosmological simulations, and you need to pay very careful attention to not only numerical artifacts but also resolution issues. And then of course, because it's abundance matching, you're relying on large scale galaxy surveys, which is great because it's data intensive. But if you care about the low mass end, you are basically stuck with only the satellite galaxies around the Milky Way or the local group. So it's a very simplistic way of connecting galaxies to halos, and it's kind of limited by lack of observations. So these is kind of the two ends of the spectrum. And I am doing work somewhere in the middle with empirical forward modeling. And I think the most kind of well-known example of this is the so-called universe machine from Peter Baruzzi. The basic idea is that you start with accurate halo density profiles, halo mass functions, halo progenitor histories, which are often taken again from these cosmological n-body simulations. That's definitely the case in the universe machine. But the idea is that you can then build a model that relates the star formation rate of these halos to, for example, Vmax or the halo, the peak halo mass at accretion, and then constrain it using observations by doing kind of this forward modeling technique. And at the end of this process, you're basically left with mock universes, hence the name universe machine. But in our case, we're left with mock galaxies in isolation. So we use, instead of cosmological n-body simulations, we use extended pressure sector theory to get at the halo density profiles, the halo mass functions, the progenitor histories of our dark matter component. And the extended pressure sector theory is a little bit involved. I won't get into it unless I get questions about it. But the idea is that basically, because of that universal subhalo mass function, you can analytically kind of write down how many subhalos are infalling in any given host for a given cosmology at any given time. And that basically allows you to construct merger trees, which are incredibly consistent with the most detailed n-body simulations. And so once you have these merger trees, these kind of accretion histories, you can initialize the orbit of subhalos using, again, idealized simulations, so that you can track how they evolve in the potential and kind of integrate their positions and velocities at any moment in time. And what's great about SatGen is that it's incredibly computationally inexpensive, right? It's a semi-analytic model, so there's no kind of heavy computation that needs to occur. The kind of only bottleneck is the actual orbit integration, which is incredibly simple because we assume that every subhalo is just a point particle. And I argue that this in combination with a model like the universe machine, in which you have a prescription for star formation rate as a function of halo mass, is actually probably one of the best ways to get at this galaxy halo connection, because it allows us to properly sample halo to halo variance. So that's just a little bit of motivation. I want to talk about some relevant observations to the work that I'm doing. So the first bit of, well, I guess I'll stop there. Sorry, are there any questions about what I've said so far? No. Okay.
Yeah. I'm sorry.
Oh, we do have a question?
Okay, I also see some participants have joined online. Okay. So
Mhm.
oh, even merger trees are not being taken from simulations, right? You do it using the press-checker formalism.
Yes, that's right. So the merger trees themselves are not taken from simulations because, again, it's a little hard to track halo properties and specifically subhalo properties across simulation snapshots. And so what's great about extended pressure sector theory is that these merger trees are kind of built from the ground up. So there's no uncertainty as to if a halo is infalling or whether it's part of a different halo or whether it's actually a halo at all. So the mass accretion histories are all taken from extended pressure sector theory. The only thing that we use in terms of that's kind of reliant on simulations is the orbit initialization. So basically we have, if you want, a PDF of potential orbital energies that we draw from for every satellite. And I'll talk a little bit about that actually later on.
Thank you.
Yeah. Okay, so some relevant observations. Hopefully some of you have heard about satellites around galactic analogs, or the so-called SAGA survey. SAGA is great because it has the express goal of kind of trying to place the Milky Way in a cosmological context, or specifically designed to answer, is the Milky Way typical? And to do that, they've observed almost 400 satellites around 100 Milky Way analogs. And this kind of shows how SAGA's footprint fits in with other similar surveys, like ELVS, for example, or satellites around the local group. What's great about SAGA is that it's a photometric plus spectroscopic survey, which means that they have really good membership probabilities for each of their satellites because they have these distances from the redshifts. And in general, they have roughly 4 satellites per host, which is not a whole lot, but it's definitely state of the art in terms of this type of survey. SAGA recently published, I think, 3 different papers, and I very, very highly recommend looking at their results. So that's SAGA, and this gives us a good handle on satellite abundances, which I'll talk about in a second. And then there's also the Dragonfly Edge on Galaxy Survey, or DEGS. This is unfortunately a lot smaller scale, only 12 nearby Milky Way analogs. But as you can imagine, the stellar halos are kind of the most extended and diffuse component of a galaxy, and so it's incredibly hard to get accurate observations of this kind of faint, fluffy component. Luckily, Dragonfly was specifically designed to image this low surface brightness stellar halo. And so what I'm showing here on the right-hand side is different imaging bands from SDSS, decals, HSC, and Dragonfly. And you can see on the bottom panel, Dragonfly is picking up the majority of this kind of extended component that's otherwise lost. And I know this panel is a little small, but basically what they can show, or what they show, is that there's significant diversity even in this relatively narrow stellar halo mass or stellar mass range, in terms of the fraction of stellar halo compared to the stellar mass. So both of these surveys kind of are what motivate me to do the work that I'm doing with the SatGen model, and I'll talk about them kind of in this order, respectively. So the first thing I want to talk about is a paper that I published last year, where, again, going back to this idea of the galaxy halo connection, really what I'm asking is, given some number of satellites and their stellar masses, what can I say about the halo masses in which those satellites live? So this is kind of the two components, or I guess three components, that build up that probability distribution function I was talking about before. Okay, so you might be wondering, how does Saga help us learn anything about, for example, the stellar halo mass relation, when you can actually observe halo masses? All you have are the satellites. Well, what Saga gives us are the satellite stellar mass function, which is shown here. Each line here is colored by the stellar mass of the host, and you can see this kind of nice rainbow effect, which already indicates that more massive hosts have more satellites or have more substructure. And of course, we already know, again, these insights from cold dark matter, what the subhalo mass functions look like, this kind of universal unevolved shape. And if we combine it with something like SatGen, which gives us the evolved subhalo mass functions, we can learn something about the stellar halo mass relation. So that's exactly what I did. What I'm going to show here are three different samples that I'll talk about for the rest of the talk. The first sample is a so-called S0 sample. Again, I care only really about Milky Way analogs. So what I'm going to assume here is that every single one of my merger trees hits exactly 10 to the 12 in halo mass at z equals 0. And so this very unimpressive PDF is a delta function at log of halo mass of 10 to the 12. And you can see what the mass accretion histories look like. Again, that variance in Z50, which is important to get a handle on. This is from 1,000 different merger trees, but in the full sample, I have actually 10,000 different merger trees. And then the corresponding halo to halo variance and the subhalo mass functions that I get for this sample. And I could do slightly better in terms of complexity, by just assuming that not every single halo is 10 to the 12. And that's exactly what I've done here for S15 and S30, where S15 now has a 0.15 dex scatter in halo mass, host halo mass, and S30 has a 0.3 dex scatter. What I want you to notice is that not only do the subhalo mass functions kind of shift towards the right, because now I'm including halos that have more substructure, more massive halos have more substructure, but also the halo to halo variance kind of puffs up with the amount of host halo mass mixing that I include in the sample. So these three samples are, again, built up from 10,000 unique merger trees that I've created using SatGen, and I can use them to create mock surveys of something like Saga. So briefly, I just want to talk about parameterizing stellar halo mass relation, which is the way that we assign stellar mass to each of these subhalos. Right now, I'll only kind of focus on the slope of the stellar halo mass relation and the scatter. So what you could do is, well, because Saga has 100 Milky Way-like analogs in it, you could combine the observations of all the different satellite stellar mass functions into a single, for example, cumulative or stacked stellar mass function, which is what I'm showing in panel C here, where, again, the unique for each host, you have a unique satellite stellar mass function, which is shown in panel B. But instead of doing that, instead of combining or stacking, which would kind of give us no information on the host halo mass mixing that I was just talking about, we use a distribution of two key statistics instead. So for 100 Milky Way analogs, we want to know what's the distribution of the stellar mass of the most massive satellite per host, and also what's the total number of satellites above some magnitude, where we think that these two observables are kind of inherent in something like Saga. In other words, there's the least amount of uncertainty in these observables. And importantly, too, we also use the correlation between panels D and E, where we think that this correlation gives us a handle on the amount of host halo mass mixing, and I'll talk about that in a second. So with some given parameterization of the stellar halo mass relation with our models from SatGen, we can combine them and make these mock surveys, and that's exactly what we've done. So this is that kind of forward modeling technique that I was talking about. Create a library of SatGen merger trees. We assume a stellar halo mass relation. We then observe the mock survey in terms of these summary statistics, sample the parameter space with an MCMC, and then compare the highest likelihood model to the assumed stellar halo mass relation. And so in doing this, we can ask two very important questions. What constraints on the stellar halo mass relation can we get from surveys like Saga? And how does host-to-host variance impact these constraints? So this is a kind of a simple parameter recovery test that we did. We played this game of like, can we recover what we feed the model? And again, I talked about alpha, which is the slope of the stellar halo mass relation, and sigma, which is the scatter. So in this panel, I'm showing the inferred value of alpha on the top versus the true value of alpha on the bottom, and the inferred value of sigma on the bottom versus the true value of alpha. And what you can see for the S0 sample is that it looks like we're actually doing pretty decent at recovering alpha, which is shown by these violin plots kind of lining up perfectly with the one-to-one line. And also in terms of sigma, we're not actually doing that bad. The uncertainty grows as you go towards steeper and steeper slopes, but in general, the median value is again kind of close to what we assumed. So what I've done here is I've varied alpha and I've kept sigma fixed. And I'll show you what the results look like for S15 and S30. All very consistent with each other. Looks like host halo mass mixing is not really messing that much with this signal. But if we play the inverse now, if I instead hold alpha fixed and I vary sigma, the scatter in the stellar halo mass relation, you can see that we immediately do much, much worse. So on the top panel, I'm showing sigma inferred versus sigma true, and alpha inferred versus sigma true. And you can see that none of these violin plots, save for maybe the 0.2 dex scatter, actually lie on the one-to-one line, and it gets even worse as you start including more host halo mass mixing. So what does this mean? It means that we can't actually get a good handle on the scatter and the stellar halo mass relation. And that's because the scatter needs to be huge in order to impact our summary statistics. So what I'm showing here in this middle panel in green is the value that we assumed for sigma versus the variance in each of the summary statistics. So on the top, it's the variance in NSAT and the variance in the stellar mass of the most massive satellite. And so you can see I wouldn't say the fiducial, the kind of standard value for the variance here is shown in the colored lines. And you have to basically crank up sigma to be, more than 1 dex before you start surpassing that standard value of scatter, basically, that's inherent just from the fact that there's more than one way to build up a Milky Way like halo. So this effect is something that we found in our paper, but it's also kind of worsened by a result from Garrison Kimmel et al. In 2017, which shows that there's actually a degeneracy between the slope and the scatter and the stellar halo mass relation. And that's because the steeply declining subhalo mass function basically means that there's many, many more subhalos at the low mass end that there are subhalos at the high mass end. And so that means that there's a higher probability of being upscattered at the low mass end than there is to be downscattered at the high mass end. And basically that results in this funny little shape here in the alpha sigma plane in terms of degeneracy. So sigma is very hard to constrain. Alpha maybe a little less so. And we can ask more questions because we've already built up this flexible model. What about future surveys? What happens if we go deeper or include more hosts? And also, maybe you don't necessarily care about the stellar halo mass relation. Maybe you want to know, what kind of host halo masses in terms of the centrals you're actually sampling. And so we played both games. Um, what I'm showing here is again that alpha sigma plane where you can see that nice degeneracy from Garrison and Kimmel. Um, and on the left, I'm showing survey depth. On the right, I'm showing survey size. Um, and basically, we play these games of what happens if my observations are slightly more sensitive to fainter galaxies. For example, instead of the fiducial value of 10 to the 6.5, we set a limit down to the 10 to the 5.5. And also, what happens if instead of just 100 Milky Way-like analogs, we have 300 or 1,000? And it looks like while deeper observations help a little bit in constraining the stellar halo mass relation, which is shown here by the kind of the crossed line, the dashed line, the true value, the real gains come from including more hosts. And that's again because really the issue is the halo to halo variance, this idea that there's more than one way to build up a Milky Way-like halo. And it turns out that 1,000 hosts, even for something as data heavy as a Saga survey that's both spectroscopic and photometric, is not actually that unreasonable, given upcoming surveys like Roman and Vera Rubin. So this is exciting. Um, it does show that as it stands, we probably shouldn't be making kind of strong inferences about the stellar halo mass relation, given a Milky Way like, or given a Saga like survey. And then we also played this game of inferring the host halo masses. So this is slightly technical, but the idea is that because I have these three different samples of S15, S0, and S30, I can kind of mix and match which sample I use to create the mock data and which sample I use to infer the real value. And that's what's shown here in the 3 by 3 cross. The point is that given a real data set, our forward model should disfavor one in which the host halo mass distributions are too narrow or too wide. In other words, given a real data set, we actually have a handle on how much host halo mass mixing there should be because of the correlation because of the correlation that we take into account across the two summary statistics. So along the diagonal is kind of the self-consistent, the data was created with S15 and the model was created with S15. And all the off diagonals show chi-squared values that are higher or lower than that. Or sorry, higher than that, not lower than that. So in other words, disfavored. And this is important just because maybe, again, we don't want to learn just about the cell mass relation. Maybe we want to learn about the underlying host halo mass distribution in our survey, which is exciting. Okay, so now switching gears a little bit to the stellar halos and the formation histories, like my abstract promised. This is work that I'm currently doing. I hope to submit by the end of the year. Here, in terms of the galaxy halo connection, what I want to learn about is the the formation time of the halo Z50, given, for example, observations of the stellar mass in the central and also the stellar halo mass, which I'll call IHL or intrahalo light. And I guess before I do that, I'll stop and take any questions about the previous section.
A couple of questions. So uh, on slide 25, you mentioned that press check formalism itself gives some scatter. Oh, sorry. So on slide 20, was it this? So I think the previous slide where you introduce your S0 model.
Yeah, okay.
So the scatter here in the background of S0 is coming from press check formalism itself, right?
Yes, that's correct.
Why does that happen? Is it because of the environment or?
Yeah, that's a great question. So it basically happens because there's a multitude of times in which you can accrete a significant fraction of your mass. So the Milky Way, for example, is expected to have a formation time of around well, I only know it in log of 1 plus e, but around 0.2, which a Z50 of 0.2, which means that at that redshift, it had already built up 50% of its mass. But there's other ways to build up a 10 to the 12 Milky Way. For example, at slightly earlier times, you might have already built up 50% of your mass and then just plateaued in terms of how many subhalos you're accreting. Or the inverse, which is, you didn't build up any of your mass until the very last second, and then you shot up to 10 to the 12. So there's just kind of this inherent variance in the way that you can accrete systems. And that's something that extended pressure vector theory allows us to take into account. So that's what the gray bands are showing there are just different progenitor histories, all of which still are consistent with a Milky Way, basically. Now, there's work being done specifically from Ethan Nadler and others, where you can kind of set up more stringent constraints, right? Maybe you had to accrete a Gaia sausage at a certain time, and you also had to accrete what's it called? Magellanic clouds
Yeah.
at a certain time, right? And that would, make the formation history a lot more tight. But in general, something that we can do with SatGen, which you can't necessarily do with simulations, is actually sample how this variance impacts your observables.
Thank you. And what are the assumptions? I'm not, or maybe we can have this discussion at the end.
Yeah.
But I'll check if others have any questions. Okay. Um, s- so one more quick question. So I
Yeah,
think
yeah, please.
on slide 35, where you talk about estimation of host mass, I don't know if it was 35 or 36. I think the
This
next,
one?
yeah. So you pick S15 here, where the scatter for halo mass,
Huh?
and then you try to constrain mass of the host using the parameters alpha and sigma. Is that what you try to do?
That's correct. Yeah, what's important is that when I actually try and do the inference, I also in the middle panel in the self-consistent or the red one that says SC, I've also used the S15 uh, sample to create the mock, right? So it's um, it's like comparing apples to apples versus the off diagonal panels is like comparing apples to oranges, where, for example, in the top right corner, I used S0 to create, to do the model, but I used S30 to create the mock data. And so there you're going to get, kind of a wider distribution in the posteriors because the the summary statistics are no longer accounting for the amount of host halo mass mixing, in this case, there's none, right? Because it says zero. That the data is showing that there is, which in this case is a lot because it says 30. So this kind of game of seeing how much we can kind of break the parameter inference was mainly motivated by Shani Daniele's 2023 paper, and that's why there's kind of two colored contours here. There's orange and blue. Orange was the method that they used that they claimed that they basically constrain the stellar halo mass relation to have a very narrow scatter of I think it's 0.02 dex, which is tiny, using only the elves survey, which I showed here. Sorry, elves is here. Elves is the local volume one, so it's the kind of one in orange where they have 10 satellites per systems, but they only have 30 systems. And this was effectively what spurred our analysis was kind of us raising our eyebrows and saying, we kind of doubt it, especially if you're not accounting for halo to halo variance in the in the modeling, which they weren't. So yeah, that hopefully that answers your
Yeah.
question. Sorry about all the clicking here. I know that I have too many slides. Um, yeah. Are there any other questions?
I guess that we have no more questions for now. So I guess you can probably go ahead.
Okay, great. Oh man. Okay, I gotta kind of go fast here. Okay. So so far I've only talked about the surviving population of satellite galaxies, right? Given some SatGen model, I can evolve them and see, where they end up at redshift 0, and if they're still alive, then I'll count them, and then I can use, a satellite stellar mass function from Saga or something to say something interesting about the stellar halo mass relation. But what about the ones that die? What about the ones that don't make it to present day? What about the disrupted satellites? Turns out that the outer regions of stellar halos should be dominated by the remains of these disrupted satellites. That's basically what builds them up. And that means that they're direct probes of the accretion history of a galaxy. And so if you look at something like the Milky Way, you'll see a whole zoo of different stellar streams and kind of tidal features that, for the most part, actually still carry an imprint of their kind of initial progenitors, or the subhalos and satellite galaxies that built them up. So in our model in SatGen, we can actually, we can't track this, what happens to the stars after they strip, because we don't actually assume anything about the stellar density profiles, but we can track how many stars are stripped. In other words, we can track how the stellar halo is built up if we just kind of put a giant annulus over it and say how much mass is within, for example, the virial radius of the host, or 2 times the virial radius of the host. So that's exactly what we've done. Again, we're not tracking any kind of post-stripping or post-stripped orbital properties of the stars. We're only tracking how many stars they lose, how many stars each satellite loses as a function of time. And so I can show you these figures that are very similar to the figures I showed before, where here I have the mass accretion history of the dark matter, but I also can track how the central component in the disk grows, and importantly, I can track this stellar halo, this intrahalo light in orange. So again, all of these kind of different lighter lines are different merger trees that I have access to, and the solid one is just the average across all of them. So what I've done here is I've actually used SatGen plus the universe machine, specifically this star formation rate versus Vmax relation that they constrain in the universe machine. And now we can kind of discuss all these different components in an isolated galaxy: the dark matter, the central disk, the stellar halo, the satellite galaxies. And these are the results. These are preliminary results that we get for the same 3 samples as before. So S0 again is the one where every single host halo is 10 to the 12. S15 is slightly larger scatter, and S30 is the largest scatter. And what I'm showing here is that kind of F stellar halo that Dragonfly or Edge, the Dragonfly survey was showing, which is just the stellar mass of the stellar halo normalized by the stellar mass of the central as a function of central stellar mass. And what's great about this is, because I have very detailed merger trees, I also know what the formation time of each of these halos are. And if I color now these distributions by Z50, or log of 1 plus Z50, you can see a very nice gradient in this space. So how can we relate the formation histories to the present day stellar halo? What can we, there's obviously information here. How can we get at it? So correlations with Z50. This is slightly, again, technical plot to explain. But remember I told you that Z50 is just when the halo forms 50% of its mass. You can, very easily also compute when the halo forms 10% of its mass, or when the halo forms 90% of its mass, which would be Z10 or Z90. And that's actually what I'm showing on the x-axis of all of these plots here. It's Z of x, where x is whatever ratio you want it to be, 0.25, 0.5 with 0.75, all the way up. And I've sampled this very finely. But on the y-axis, I'm showing the correlation between each of these components: M central, MICL, MSAT, the accreted component onto the central galaxy, versus that formation time, versus Zx. So what this basically shows is, if there is a correlation with any of these components as a function of the fraction of mass that you've already formed, this should basically show up as either positive or negative, non-zero, basically. And I'm also showing it for all three of the samples. So just looking at the top panel, you can already see in the S0 sample, the green line, there's a very strong correlation with Z50 and the central stellar mass, right? That's good news. It looks like as you go to S15 and S30, that correlation actually kind of diminishes. And that's again because we're including more and more host halo mass mixing. So now the correlation between Z50 and M central in the S30 sample, for example, is less strong because really what sets the central stellar mass, or sorry, what really sets the formation time is the fact that you have a more massive halo than 10 to the 12. Similarly for ICL, it looks like there's a strong correlation with Z50, a strong negative correlation with Z50 and the ICL, and it kind of then diminishes as you go towards uh, higher and higher mass fractions. What's interesting too about now the third panel MSAT is that it looks like the strongest correlation isn't actually with Z50, it's actually with Z90, which makes sense because Z90 is a kind of how can I say this? It's a more recent age indicator than Z50, and basically these satellites disrupt pretty quickly within, at least for the Milky Way, within 2 GeV generally for most orbits. And so if yeah, if your Z90 is pretty small, for example, you would expect to have a lot more surviving satellites, and that's what's showed here in the correlations. So this is great, right? We have all these different components. We can see how they track with formation time, and in our fiducial model, it's actually inherently simplistic. Basically, we just assume that whatever the halo mass is, you get some star formation rate, and that is of course integrated across cosmic time. That's what builds up your central stellar disk. And so there's going to be always this very strong correlation between Z50 and M central, which is what I'm showing here on the bottom right panel, which of course gets muddled as you move towards more and more host halo mass mixing in S15 and S30. So the question is, maybe we can combine some of these different observable components to infer Z50. And right now, the way that I'm trying to do that, this is very preliminary, is using random forest regression. So what I'm showing here is the predicted value of Z50 versus the true value of Z50, and then also the residuals. Given some regression model that I've trained on just the S0 sample for now. And it looks like we do a pretty decent job at recovering, what the true value is if I only feed the regression model these three components: M central, MIHL, and MSAT. And what's interesting is that the central component, M central, is by far the most dominant feature in terms of the information content that it has. If I move away from my fiducial universe machine model and I just randomly assign a stellar mass, for the central disk based on the stellar halo mass relation, we still actually do a decent job at recovering Z50. But you can see that MIHL and MSAT actually take up the slack because now M central is not at all correlated with the formation time. So there's these different games that I can play given this random forest regression technique. And what I'm finding, at least preliminarily, is that you can do a decent job at recovering Z50. This is, of course, in the most simplistic model, S0, with a very easy to understand link between the star formation rate and the halo mass, which is, of course, probably not how the universe actually works. But in any case, it's very promising to see these types of results. And like I said, I'm going to talk a little bit about orbit stochasticity. So I can play these games where for the same exact merger tree, I can, instead of assigning one realization of initial orbital properties, I can assign it multiple. So basically what this means is I can take the same exact formation time, same exact Z50, but just give every single satellite or subhalo that falls in a slightly different orbit, slightly different orbital energy. And what I'm showing here on the bottom left panel is the distribution of MSAT versus MIHL with these two different samples. So S0 is just the standard S0, but SC is this one that's constrained to have this exact same Z50. What's curious about it is you can see all these different peaks, right? Now it's not this nice kind of more or less uniform distribution. It has these kind of multimodal these peaks, and that's actually because um, it actually basically comes down to whether you have your most massive satellite surviving or whether you have your most massive satellite disrupt in terms of what orbit you give it. So what I'm showing on the top panel now is the distribution of IHL just kind of cut at where I see this little this double peak. And then I colored each of these samples based on the stellar mass of the most massive satellite, and also the pericentric distance of that most massive satellite. And you can see that basically these distributions trace whether this most massive satellite is still around at the end of the simulation and how far in it got relative to the host halo at the end of the simulation. So basically, a higher MSAT would be that satellite is still around. It did not disrupt, which would, of course, trace to a slightly less energetic orbit in the sense that it has weaker tides. And what's great about this is that it shows that orbit stochasticity is actually incredibly important in terms of how much variance you expect in these two distributions, in MSAT and MIHL. Despite the distribution being very multimodal and kind of funky, you can see that it actually, in terms of a minimum maximum, traces basically S0, which has 10,000 different mass accretion histories, whereas this one only has the one. And finally, we can also play these games of, how does the stellar halo mass relation that we assume impact the results? How does, the universe machine stellar halo mass relation we assume change these different components? So I'm now plotting M total, which is the MSAT plus MIHL versus M central. And I'll just kind of run through this very briefly. You can see that the slope for this blue line here is 0.5, so very, very shallow. And as you go towards steeper and steeper slopes, these distributions change. And this is actually a result that Martin Ray showed in 2023 with their genetic modification code. And it's very kind of encouraging to see that we can recover a similar result, which is basically that the steeper the stellar halo mass relation, the less amount of mass you have to contribute to the stellar halo, and therefore you get this kind of narrowing distribution as you increase towards shallower stellar halo mass relations. And so, yeah, with that, I'll conclude. Sorry that I know we're just right at time, won't have that much time for discussion, but I think that semi-analytic and empirical forward modeling techniques are well suited for studying the low mass end of the galaxy halo connection. There are new and exciting observations that will help us with these inferences, specifically SAGA and also the Dragonfly survey. We developed a model to simulate satellite galaxies and stellar halos using SatGen. And it's what we showed in my 2024 paper is that it's going to be difficult to place meaningful constraints on the scatter and the stellar halo mass relation with current observations. And what I'm showing now, hopefully, which will be submitted soon, is that there's a clear correlation between the mass of the disrupted remains of accreted satellites, or MIHL, and Z50, which maybe we'll be able to get a handle on given some observations. And with that, yeah, thank you very much for your attention. I'll take any questions.
Not yet now. Let's clap now. It was questions. Hmm? Oh, yeah. Online participants, I just wait if there are any questions from others. Okay, so let me ask, there, I think, so I do not exactly remember the suite of simulations, but
Yeah.
on Milky Way scales, I guess, I think there's a team at Flatiron who which has been trying to simulate like thousands or tens of thousands of Milky Way mass, or maybe dwarf galaxies. Um,
Yeah, I think you might be thinking
Train
of
ML models.
with machine learning, you said?
No, no, I think they're trying to train ML models using this.
Ah, okay.
Would you be able to test the SatGen model with their simulations? Because I'm assuming within the model, you still wouldn't be able to model something. I'm assuming the tidal stripping and other, uh, I mean, other processes are assuming like pure spherical symmetry or something like that
Yeah,
without.
yeah, yeah.
So, do you think you'd be able to compare it with simulations or?
Yeah, it's a good point. Basically, the simulations are great. Yeah, I know I was just spending some time talking about what's not great about them, but the simulations are great because they're actually, tracking what the gravity does. And of course, it's dependent on the mass resolution. But in general, what we can't do with something like SatGen is say, yeah, what happens to the stars after they're stripped, and also how they evolve within the potential. And so what we're doing basically underneath the hood is assuming analytic prescriptions for how the mass of the subhalo decreases as a function of time and as a function of the uh, of of the tides, and then tying our stellar mass loss rate to that dark matter mass loss. And so it's inherently very simplistic, and it'd be very interesting to compare to something like a hydrodynamic simulation. What's important though is that it's difficult to make that comparison because of the uncertainty in simulations for tracking these properties across snapshots. And so I'd be very, yeah, interested to know. I think you might be talking about the Edge simulation suite. It's like something about dwarf galaxies. It's like the edge of dwarf galaxy formation or something. They have someone just came to give a talk in our department. They have, I think, upwards of 100 or so different realizations, and they're incredibly computationally expensive. It's they're still running a lot of them, but I do plan on trying to make a comparison with something like that. Because yeah, our model obviously has to cut corners in some places, and one of the main places we do that is with the orbital evolution.
But it's like genuinely interesting that everything is fully analytical. I don't think you use simulations.
Yeah, the only
You
thing
use
that's
simulations
not.
for only for orbits. Is that right?
Yeah, and yeah, the only thing that we're doing is like a numerical integration of a point particle in a static potential. Well, not static. It does grow as a function of time, which makes it a little complicated, but that's the semi part of the semi-analytic model, because the rest of it is fully analytic. Yeah.
Interesting. Uh, Amazing work. I'll just check if there are any questions from online participants. Yep. Mari has a question.
Yeah.
Hi, Jose. This is Marie.
Hi,
Very
Mary.
nice talk. I guess my question isn't quite about this talk, but I think your career trajectory will be inspiring to other people in this audience too. I know you spent some time at NASA Ames, and that's between your time at Santa Cruz with Prochaska and me and other people, and then
Yeah.
you started a different project at Yale. Can you talk a little bit about your experience at NASA Ames doing a completely different project and then getting into graduate school? I appreciate your perseverance and resilience. Can you talk a little bit about that?
Yeah, yeah. Sure. Well, yeah, so I did my undergrad at UC Santa Cruz, where I worked with Xavier Prochaska for, well, it was like 3 years, two of which I did an REU program over the summer. One of those was when I worked with Marie. And after finishing my senior year, I didn't actually know if I was, certain about applying to grad school. And so I took kind of a gap year or a post-bac year, and I applied to work at NASA Ames, which actually turned out to be quite the blessing in disguise, because that's when COVID hit, and so a lot of students actually started their PhDs during that time, which I know was difficult given the online classes and everything. But I was able to work remotely basically over the next year and a half on several different projects, all of which were related to kind of high mass star formation, or ISM astrophysics, basically. And I realized I didn't love, and it was all very observational. So it was using the Sophia instrument, which is like this observatory on a plane. It's no longer running, unfortunately, but they would basically fly this Boeing 737 or something that had a hole cut out of it, and do very interesting science in the mid-infrared. Um, Anyways, I realized I didn't love kind of drawing conclusions about certain things given, a single sight line or given a single young stellar object. And I wanted to do something slightly more theoretical, and also slightly kind of bigger picture in scope in terms of like the question that we were asking. And I think dark matter is, this massive question. And so when I applied and got into Yale, I was very excited by all the galaxy formation faculty that teach classes here, and was most impressed by my advisor's course in the theory of galaxy formation. So I started working with Frank in my second year. At Yale, we have these rotations. And in my first year, I was working with Marla Jiha. And I got initially very interested in kind of the low mass end of the galaxy halo connection because of that first year project. And then once I was working with Frank, I kind of transitioned more into the theory side of things. But yeah, my trajectory has been kind of all over the place. When I was working with X, I was working on high redshift, Lyman break galaxies, and kind of the effective opacity of the IgM. And then I went to star formation, and now I'm working on dark matter and the galaxy halo connection. But it's been I think really important for my career to kind of have that middle section where I got to really decide if I wanted to go to grad school, and also try on a different style of research. It was very inspiring to be around all those NASA scientists. And yeah,
Thank you.
of course. Yeah, thanks, Marie. It's good to see you.
Hey, thank you again for accepting our invitation.
Yes, thank you for having me. And I'm actually the coordinator for Yale's Galaxy Lunch. It's a weekly seminar that we have every week during the semester, basically every week during the semester on Wednesdays. So if any of you are around, the East Coast, around Connecticut, and want to give a talk, please reach out to me. We're currently making the schedule for next semester. So if you happen to be around, I'd love to have you.
Definitely.
Okay.
Thank you so much. We'll
Yes.
share, so we'll post recording to YouTube if it's okay with you, and then we'll share it with you.
Sure. Great. Thanks again for the invitation.
Thank you so much. See
Bye-bye.
you.